All right, hello everybody. In this video lesson, we're going to go through how to measure the speed of sound. So in the past lesson, we looked at measuring the speed of a wave in a spring. This will have some similarities actually. It's just you can't see the wave the same way. And so instead you're using our knowledge of wave properties of sound. This is something I show when we're doing the lesson in person so that we're getting the right sound. You have to hit a tuning fork so that it has like the fundamental pattern, which I showed the strobe light video of, because you can get clang mode, which is higher frequencies from higher frequency patterns showing up or shorter wavelength patterns showing up. And so if you look at the fundamental mode of vibration, I did this one year where the fundamental mode of the tuning fork showed this frequency. And then when you hit it harder, it made like this ringing, clanging sound. And it had the fundamental, but it also had a bunch of other ones. And so you might hear resonance of these sounds instead of the pure tone. And this is something that exists in the world just around us as well. You might have seen this video on social media of some sort as well. This giant tuning fork, I kind of want one. So that is undergoing like a very complicated clang mode vibration if this video is legit rather than just being AI or photo, whatever, manipulated. But that relates to it. So I thought I'd show it. And so if you were hitting a tuning fork over an air column and listening for resonance, and then we're going to use that to show how to measure the speed of sound, you want to make sure you're listening for the pure tone, not these other harmonics, or else it'll drastically mess up your measurement or your conclusion for the speed of sound. So I found this video, and it's very much what I was thinking of doing. And so watch this video, and you'll see different parts of the video. Let me just click on it. He literally just says, hey, I'm doing the speed of sound and air. He does a pretty good job as well of showing I'll just go through here. Pretty good job of showing like the wave patterns like I've done as well. He ends up focusing a little bit more abstractly on the generic formula with N. I'd much rather you just think of like the first resonant length. The length you're talking about is wavelength over 4, and so it's equal to whatever length you see in the video, and you just multiply by 4 to get your wavelength. And then for the second one, there's this pattern, so that's 3/4 wavelength, and so whatever length you see in the video, just like I did with the spring stretched out. This is very similar to the spring wave speed video that I made. I was thinking of making one. It's hard. I have a hard time getting my microphone to pick up the sounds, as you might have noticed in the previous video lesson. And so he's got to set up somehow that you could hear it better. So I'm going with this one. But yeah, this just the length you see in the video, multiply by 4, divide by 3, rather than focusing on this abstract formula where he says, oh, in general, the length equals, n lambda over 4, or you could solve for lambda behind his back here. You can see that somewhere at some point, right? So instead of doing that, I'd highly recommend you just sort of think about it a little more logically in terms of like what pattern we have, therefore you know what the length is, and you just solve. And there's actually just a help video I just posted responding to this because the process of doing this calculation is exactly the same as the process, just different fractions, right? As the process that was used with the figuring out the wavelength based on the spring standing wave pattern. So that's one change I would recommend, is not worry about the abstract N4 over L business. Really, you're just going to get wavelength, right? And then you're going to calculate the speed based on, the wavelength. So you have V equals F lambda. You have the frequency of the tuning fork, and it says it is in the video, because there's a speaker as well, I think, times the wavelength. And so in your tables, you just have results from those calculations rather than the way he shows it. Hey, but in this video, he shows, let me go. Oh, this is good too. He shows, the closed end of the pipe being the node, the open end being an antinode, and then the Walter Fendt applet that shows this nicely. He shows as well. And he reminds you that a node is a spot where the air molecules aren't vibrating back and forth. You can see the same thing on the end there. and then a spot where they are vibrating back and forth. Just a reminder that that's really what's going on in the air column. But we draw like this just out of, for simplicity, right? To understand what we're looking at. And then he just, does the lab, right? And so you can hear where the resonance gets louder, gives you what the frequency was, and so on and so on. And that one, I think, just jumped through. You have to maybe slow the video down. And right here, right there was a first resonance. Second resonance. So on and so on. So you're just listening for resonant lengths. And then the first resonant length, of course, is this math, this pattern, this math. And the second resonant length is this pattern, this math, and so on. And so you get wavelengths paired up with corresponding frequencies, and that's going to allow you to measure the speed of sound. Surprisingly easy, really, based on understanding of resonance and amplification of the sound. And so his table looks different than I'm hoping yours will, because really you can just say, okay, well, for the overall length is known. It's just the length from the video that you see, right? And then your idea here of like the wavelength. This would be the wavelength category in his, but you're just going to do what I showed you earlier in the video. Just calculate the numbers. So organizing that table, you're going to have to decide how you're going to organize that stuff. I would have two sections for each frequency. Like if there's 512, let's say, and there was a first resonant length and a second resonant length, I would have a section for the first resonant length and a section for the second resonant length. Then you can just show a result here for wavelength, and with a sample calculation like normal. You don't have to show every calculation. Just show a sample calculation like the ones I'm saying to do here, where if this equals 38 centimeters, well, it's going to be times 4. So the wavelength would be whatever 38 times 4 is. Okay. So that is the measuring the speed of sound portion that is listed here. So using properties, measuring the speed of sound, the purpose of the lab is measuring the speed of sound. And so method 1 is using resonance and air columns. So that's this, using a known frequency. You can hold this is just the basics of what we did. When I was doing it with a class, of course, it was sending them into the lab to do the work. So this is just a description, but it might help you keep track of what the heck's going on. And the other method would be just to try and measure it directly, measure the speed of sound directly. And of course, the main difficulty is it's really fast, right? Speed of sound is really fast. And so the time intervals that you're measuring are crazy small. So if you tried to measure echoes directly, you're going to have a distance that you're hearing an echo from. So I guess the distance would be there and back, right? So maybe it's 500 meters or something, or less, probably 200 meters would be a lot. And then the time is going to be very fast, and so you're measuring something like 0.8 of a second, give or take a half a second. The percent error is pretty terrible. And so there's ways that you can improve that. And so one method is that period echo clapping method. And there's 2 videos here that if you click them, show the idea of that. I'm going to show a bit of this one to start with.
Using some wooden blocks and a wall. We take a measuring wheel to measure the distance between this man and the wall. Let's say that's 100 meters. We give this man 2 wooden blocks, or a wooden clapper if you got one. Then we stand right next to him and have our timer ready. When he claps the blocks together, the sound wave of the clap will travel towards the wall. It gets reflected at the wall and then travels back towards us so that we can hear its echo. So we're going to start the timer when he claps, stop the timer when we hear the echo. Ready?
They're showing it taking like 0.58 of a second, and then your thumb pressing the button is give or take a half a second. So it's terrible, obviously, percent error wise, right? But the concept is very simple. It's just distance over time and so on. So because the error is so bad, percent error so bad, the reaction time is like 0.25 of a second or 0.5 of a second. I often hear as well. The idea is what's called period echo clapping. So we're going to look at
to clap the blocks 10 times. After the first clap, the sound wave travels there and back. And when he hears the first echo, he claps a second time. After the second echo, claps a third time, and so on. It'll probably take him a bit of time to get into the right rhythm for synchronization. So you end up like tuning it so you're clapping in sync with your echo. And so the other video shows this as well, and it's a class with a teacher out doing it. And so I'd like to have you do that activity. Find a spot where you can get the echo from a building, a barn, or house, or whatever, and just save your hands and have 2 blocks of wood to make a loud noise. And you'll see in watching these videos the idea of how to do it. Basically, you can get a frequency from this, which you can work out to be a period, which is the time it takes the sound to go there and back, right? And so you have a distance and a time. Definitely based on stuff we've done in the course, and so it makes sense to include and get you to work your way through it, all right? So the first part of the lab is data from watching this video. The second part of the lab would be you measuring, because I don't think you can use the data from this one. It didn't seem like it was like made to be that way. So you'd have to actually, get a stopwatch and do some clapping. You might have to get a friend to help you out. It's a little hard to clap and start the stopwatch and so on at the same time. Okay, so try your best at that. See how it goes. So this is another lab. I have, the first lab isn't due yet, even because of people late entering to the course, but this one's going to be after that. So the plan would be for you to have feedback from the first lab before this one's due, so you can work on improving. All right. So that's it for that. And yeah, let me know if you have any questions.